In the next series of videos, we're going to start on part 3 of the APES review guide, and that's the population part. The population part is going to have quite a bit of math to it, but the math is more or less basic, just like addition, subtraction, and stuff, so it shouldn't be too bad. Again, these are all rules that these are all terms that I totally expect you to know, right? Age structures, carrying capacity, birth rates, death rates, how you calculate growth rates, all of that stuff. So all of these are terms that you should be familiar with. On this first video, we're going to go through section A. So we're going to look through just some basic population biology concepts, right? We're not going to get into any of the specifics. This is just going to be an overview of the basics of population dynamics. I'll start with the first one. So we need to draw and label a line that represents linear growth and draw and label a line that represents exponential growth. Well, over here, our red line is our linear growth line. So this is our, right, linear. And then our blue is our exponential growth. So in the linear line, the slope never changes. In the exponential growth curve, the slope continues to increase as time goes on. There are quite a bit of examples of exponential growth. The most common one is probably this graph of carbon dioxide concentrations. So the amount of carbon dioxide in the atmosphere has been increasing exponentially since about, the start of the Industrial Revolution. And the biggest increases to carbon dioxide have happened quite recently. So moving on. Let's look at the 4 most populated countries in the world. So right now, as of the recording of this video in like mid-2020, I guess, the most populated countries are going to be China, India, United States, and Indonesia, in that order. Both China and India have populations of greater than 1 billion. The United States is not quite anywhere near 1 billion yet, but those are the 4 most populated countries in the world. You should probably know those off the top of your head. So now let's finally get into logistic growth. And logistic growth is the most commonly occurring type of growth we'll see in ecosystems and in natural systems, right? We have this period of slow growth followed by a rapidly increasing population, right? And this section here, where the population is growing at its fastest, right? Where the slope is the highest. This is considered the biotic potential. The biotic potential. And what that means is that this population is growing as fast as it possibly can, right? It's at its full biotic potential for growth rate. But then it starts to slow down and you get to this carrying capacity, right? An ecosystem cannot infinitely sustain a massive, infinitely growing population. So there comes a point where competition for resources, competition for mates, density dependent factors such as disease spread start to even out how big a population of a particular species can get, right? And that's the carrying capacity. Now let's just do a little math problem. Here it asks us to calculate a growth rate for a population. And we know the general growth rate formula. You're taking the birth rate plus the immigration rate, and you're subtracting from that the death rate and the emigration rate, and that will get you the growth rate for the population that you are studying. Now, this formula right here has it as just birth rates. Remember that there's 2 different ways to look at birth and death rates, right? You can do it as a crude birth or death rate, and those numbers are out of 1,000. So if a population has a crude birth rate of 3, that means that there's 3 births for every 1,000 people, right? Crude rates are out of 1,000. And then there are percentages or percent growth rates. And those are out of 100, right? All percentages are out of 100. So if a population has a growth rate of 3%, that means that there are 3 births for every 100 people. So when you're looking at a problem like this, you definitely want to pay attention to what the answer asks you for. And here, the answer is asked to be in a percent. So we have to get everything into units out of 100. So to get a crude birth rate of 45, which is out of 1,000 to 100, you just move the decimal place over, divide by 10, right? However you want to do it. So the actual birth rate, so the percent birth rate, ends up being 4.5. And the crude death rate is 20. That means the percentage death rate is going to be 2.0, right? All we did was we moved that decimal over. And now we can plug these right into the equation because the immigration and emigration rates are given to us in percentages already. So now we just plug it into the formula, right? The growth rate for this country is equal to the birth rate, which is 4.5, plus the immigration rate, which is 1%, minus the death rate, which is 2.0, and the emigration rate, which is 0.5. If you add all of these together, or technically subtract all of these together, you get a growth rate of 3%. Now let's do some other basic ideas of ecology here, and that's R-selected species and K-selected species. So R-selected species tend to have a relatively short lifespan, and they tend to have many offspring with very little parental care, right? An example of an R-selected species is like a fly. They have lots and lots of offspring. They're not really raised in any way. They have short lifespans and they reproduce in large numbers. That's the reproductive strategy, right? Reproduce with as many numbers as you can and hope some number survive. That's the idea of an R selection, of an R selected species. The exact opposite of that is K selected. So these organisms tend to have a very long lifespan. And they tend to have very few offspring, but they invest a lot of energy, a lot of parental care into making sure that offspring survives. An example of that would be like elephants, right? They have very few offspring, but they put a lot of effort into making sure whatever offspring they do have manage to survive. So if we're looking at survivorship, we got to look at survivorship curves, right? And there's type 1, type 2, type 3. A type 1 survivorship curve is very typical of a K-selected species, right? You have some sort of offspring and you make sure that it survives for as long as it can. So you have really low death rates early on in the age of a K-selected species. And then you get high death rates at the older it gets, right? The older a K-selected species get, the more likely it is to die, just out of old age. Our selected species are the opposite. You have really high death rates early on in life. You have huge amounts of death very early on in life, but then some number manage to survive to old age, but not nearly as much are born. And then there's this weird type 2. Type 2 is like your chance of death is pretty much equal no matter where you are in life. That's just really what it means. What kind of confused me here is I kind of missed this when I was putting things together. It asks you to label the environmental resistance and biotic potential. Those are terms for growth curves, not survivorship curves. So survivorship curves show you how many of a species survive over time. Environmental resistance and biotic potential look at growth rates, right, which look at how quickly a population grows over time. So again, biotic potential is this part where a population is growing at its fastest possible rate. Environmental resistance is, I don't really even call it that. I call it equilibrium, right? A population remains stable. It's resisting environmental pressures, right? It's going up and down and going up and down, but it's more or less staying at equilibrium. So I don't even really use this term environmental resistance. I prefer the term equilibrium, where the population stays at a relatively, stable size. And then next video, we're going to go ahead and get into human population. So we're going to put a little bit more focus into how human population growth rates and how human populations work. Virtually the AP Human Geo segment of environmental science. So here's a video of what I did before shooting this video.